In this short video, I just wanted to go over the expected value of the Poisson distribution. This is a classic example that you see if you take a course in probability. So we say that a random variable x has a Poisson distribution with parameter lambda if the probability that x is k, so this is a discrete probability distribution. This is equal to e to the minus lambda times lambda to the k over k factorial for k equals 0, 1, 2, and so on. And lambda is some positive number. That's the definition of the Poisson distribution. Now let's check that this is actually a probability function. So we need to sum over all values of k. Well, recall that e to the x has this Taylor series expansion. It's the sum from k to infinity of x to the k over k factorial. So e to the negative lambda is the sum from k equals 0 to infinity of x to the minus, let's see. Yeah, you just have this issue with real numbers. I guess this isn't an issue because I was going to say you have this issue with raising negative numbers to powers, but since the powers are integers, this isn't an issue. Okay, so this is negative lambda to the kth power over k factorial. So when I take the sum overall p of x equals k from 0 to infinity, I get this doesn't seem very obvious that the sum is 1, is it? Oh, I see how it works. Okay, the point is that this is the sum so sorry, I have e to the lambda is this. And then when I take the sum from k equals 0 to infinity of e to the minus lambda, lambda to the k over k factorial, this e to the minus lambda is a constant, so I can pull it out, and then I get this. There we go. So this is e to the minus lambda times e to the lambda, which is 1. Okay, right, because it's e to the 0 power, e to the 0 power is 1. Now let's find the expected value of this distribution. So if x has a discrete distribution, then the expected value of x is defined to be ex, well, that's defined to be the sum over all x of x times the probability the capital X is little x. So what does that look like in the case of the Poisson distribution? In the case of the Poisson distribution, we have x as a Poisson distribution with parameter lambda. What we have to do is we have to sum overall k of k times the probability that capital X is k. Well, when k is 0, this product is just 0, right? So we just need to sum from k equals 1 to infinity, so we get k times, and the probability that x is k is e to the minus lambda, which we can factor out. So you get e to the minus lambda here, and then, what was it? The probability that x is k, lambda to the k over k factorial. Okay, lambda to the k over k factorial. Now the question is, what is this sum? There's always these tricks. I see. There's a trick which is to factor out a lambda from the top. So you get lambda. The trick is not to factor out the e to the minus lambda. Okay, the trick is to factor out a lambda, and then you get the sum from k equals 1 to infinity of e to the minus lambda, lambda to the k over k factorial. Now this sum, no, it's a k minus 1. Okay. So now you have this lambda to the k minus 1, and then you have so I'm trying to make the sum look like a Poisson distribution. But I think I have to factor out a k. So I'm going to have something like k times k minus 1 factorial. So I know that when I have this sum, the sum of all the p of x equals k, I get 1. So I know that if I take I see I have a k here. Sorry, I have a k here, and then I can cancel out the k's like this. And then when I take this sum, this is just the sum. Like I'm re-indexing starting with k equals 1, right? So like this would be the sum from, say, u equals 0 to infinity of e to the minus lambda, lambda to the u over u factorial. And then I know that this is equal to 1. That's the calculation we just did. And so the expected value of x is lambda. Okay, so I should not have pulled out an e to the minus lambda here. I should have kept it on the inside. So there's this re-indexing trick. It's okay, e to the minus lambda, lambda to the k over k factorial. The point is that you can cancel out one of the k's, you pull out the lambda, and then you get a sum. And this infinite sum comes from the Poisson distribution. And we know that the sum is 1. That's the calculation that we did here. So the expected value of x in the case of a Poisson distribution with parameter lambda is lambda.